Okay, good afternoon. Let me start by thanking our hosts and the members of the organizing committee for all the hard work setting up this workshop. Like Dr. Zavala said this morning, these types of opportunities, unfortunately, are few and far between. So I'm really thankful for the opportunity to speak about our research. I'd also like to start by acknowledging, excuse me, the students that have worked with me in this past decade. We'll be seeing some of their work in this presentation, so thank you to them as well. So a major theme of this workshop is probably going to be to show just how the underlying theories behind monsoon circulations are evolving even after the monsoon systems haven't been recognized for such a long time. There's a huge amount of research and history related to monsoon systems. So it's remarkable that even after so much time, the underlying theories are still evolving. This is the seasonal precipitation differences. So the boreal summer minus winter from ERA 5. And it clearly shows what is now well recognized as being the 6 major monsoon systems of our planet, 3 per hemisphere. Obviously, the East Asian monsoon is the most famous and largest of them all. And in this talk, I'm going to focus on the North American monsoon. The term monsoon has probably become an umbrella concept that covers a range of physical processes. And I hope to illustrate with this talk this aspect regarding the North American monsoon. So if we make a zoom here over Mexico and Central America, I guess one of the first questions that we can make about this monsoon system is it a single system or is it actually two? We heard David talk this morning and refer to the North American monsoon as something that essentially begins more or less around the state of Nayarit and spreads along the Sierra Madre Occidental into southwestern United States. But if we look, so if we zoom out and we see how precipitation changes seasonally, we see that this region, what we, after David's important paper in the 1997, which is probably where the term North American monsoon, at least as we understand it, was began to have traction. Well, like I said, we might ask ourselves, is this part of the same system or is this two different systems? So there's this paper in 2002, these authors, Hu and Feng, began to answer this question. And what they're proposing is that it, in fact, is two separate systems. They looked at using a same methodology that I'm going to show you in some results here, which is working with climate indices and then using linear methods like correlation maps to try and distinguish different processes. In this case, this is one of such correlation maps. They are comparing an index that gives the ITCC location over the warm pool region west of Mexico and rainfall over the JAS summer. And so what they're arguing is, look how correlations are, cross or near zero over the Sierra Madre Occidental. This is correlation of precipitation to ITCC latitude. And they grow to a significant level southward. So we have this antecedent result, no? that is suggesting that what currently, especially in literature that is trying to answer questions about climate change and using, for that regard, global models, this results of the SEMI-6 models, what is referred to as the North American monsoon in those papers, they look at a global scale. It looks like it might, in point of fact, be two separate systems. Okay. Also, working still on the giving you some antecedents of to set up the main subject of the talk. I'd like to point out these couple of papers, which to me have always been extremely interesting, and also serve to illustrate what I meant by the term monsoon actually being an umbrella term that covers a range of physical processes. So Rodwell and Hoskins, in these two papers, what they did was use diabatic heating as a concept. I didn't hear it come up yet this morning, but so obviously we heard a lot about adiabatic processes, right? So diabatic processes would be those that are introducing or subtracting heat from a system, an air parcel. And in itself, it would be difficult to assess it from the results of a model, of a global model. So what they propose to do is calculate diabatic heating as the residual of all the other terms of the thermodynamic equation, which can be readily computed from the results of a global model. And here we see a climatological map of Q averaged. The diabatic function obviously is three-dimensional. It enters and exits air parcels at any height and at any place in the planet. But here the authors reduced it to a vertical mean. And we're looking at the summer. How does the climatological mean Q look over the planet? And then what they did to prove their point, also let me say one quick thing about this. It's very important for tropical meteorology. So on the side of theoretical development, there is a very important paper by Professor Adrian Gill in 1981, who used a linear simplified shallow water model to obtain analytical solution for the problem of the atmosphere responding to localized diabatic heating. And basically, it's a very similar model as is used in other theoretical frameworks for the tropical atmosphere. Matsuno, in his famous development of equatorial waves on the equatorial beta plane, used pretty much the same model. No? But Professor Gill then gave the result for a model, for a shallow water model that does permit horizontal variations in density, which is in itself a remarkable result, very important from a theoretical point of view. And what he came up with is essentially the atmosphere response with emitting a Rossby wave towards the west and a Kelvin wave towards the, I guess I said it the other way around. No, yeah, Rossby wave propagating west and a Kelvin wave propagating east on the equatorial beta plane. And so now here, Rodwell and Hoskins are arguing, well, let's see what happens in the subtropics outside of the equatorial channel. And they used idealized modeling in which, so they have their global model, but they play with the Q function, with the diabatic heating. They do an integration of the model without adding heat, Q set to 0 everywhere, only having topography. And then they progressively add different terms of this Q function the Q in the North American region, like these letters indicate. And what they come up with is an ever more realistic atmospheric circulation. Basically, they produce the anticyclonic, low-level anticyclonic circulation over the Pacific. So, just to finish with this point, in Rodwell and Hoskins, as in there are other examples, I'm sure, the term North American monsoon absolutely does not refer to the same thing as what we've been talking in the morning. North American monsoon for them is the seasonal changing in atmospheric circulation that arises from migrations of the large-scale subtropical highs on either hemisphere. Okay, so that's, I guess, enough backdrop to my talk. So let me start showing you some of the results that we have been working on, specifically regarding the North American monsoon. The first thing I want to show you is taking a lead or following the lead from Rodwell and Hoskins. We did an update of this Q function, now from a modern reanalysis. This is from ERA 5. So calculating Q as the residual of these terms of the thermodynamic equation. And here you see also, as in the previous figure, a vertical mean of Q and a climatologically average for the summer. And you can see there are several similitudes, it agrees well with what they found 20 years prior. But what we can do with this Q function is use it as a climate index and ask questions about how the system works. I guess also following Hugh and Feng, just calculating correlation maps. So a first correlation map that is more of to check if we did the calculations right. It's an obvious correlation. Is correlating at every grid point of the ERA 5 grid, correlating what we got for Q versus the precipitation that the same reanalysis product produces. And as you can see, it's nearly perfect correlation. It's obviously higher over the ocean than it is over land, I guess for reasons very similar to what you were arguing about how topography modifies convection, introducing a different nature to the problem. But the other thing that we can do is correlate area average Q against precipitation. And in two regions, over here, over the Pacific Western warm water pool, and over what is widely regarded as the core region of the North American monsoon. And the results are, I guess, encouraging in the vein of what Hugh and Feng proposed also 20 years ago. This does seem to be like two systems acting separately. One more correlation just to prove the point is actually recreating Hugh and Feng's result, but with the ERA 5 database. And so this is correlating an index for the average position of the intertropical convergence zone against the precipitation over the summer season. And you can see it's highly correlated in the region of where the seasonal range of precipitation is greatest, and it pretty much goes to zero over the North American monsoon region. Okay. This talk had in the title Mechanisms for Interannual Variability. I guess I'm probably already halfway there, and I haven't even said anything about that yet. Happens to me that I'm not very good at managing time and in 1 hour talks. But anyway, So one last correlation map to illustrate how this diabatic function can be useful for climate studies. This is this Q function correlated against different climate indices that represent what we know are the main modes of climate variability. Obviously, the leading one is ENSO. For that, we have this Oceanic Niño Index, which is an index that combines information from SST regions in the equatorial Pacific. There's a large list of climate indices maintained by NOAA, no? But just to put two other examples, the one for the Arctic Oscillation, and this is the North Atlantic Oscillation. So another important source of variability that is obviously centered in the North Atlantic. So you can see how these indices correlating against the Q function compares. And again, probably a result that we would expect. Greatest correlations are with El Niño, not only because of these three phenomena. The ENSO has its epicenter in the equatorial Pacific, therefore it is closest geographically to the region that we are studying. But as in the region of the North American monsoon, ENSO correlations are of greater magnitude, and very interestingly, they change sign several times in this region. So what does this suggest to us is the physical mechanism that is tying ENSO with the heating, the diabatic heating, is not probably not a simple one, but rather something complex. And another point to make about the correlation crossing signs in this region. So if you have, obviously, when you're calculating correlations, you're interested in whether or not they are significant. If you have significant correlations on both sides of zero, this is a good indication that probably the whole map is referring to something that is physical, not noise. Because if the process that is responsible for these linkages is such that it is directly proportional in some geographic region, but inversely proportional in another region, then you obviously expect the correlation to cross zero. In other words, to pass through a region where it would, if you do a statistical testing, you would get the result that is not statistical because the value of the correlation is too close to zero. I don't know if this explanation was clear to you. If not, I'm happy to speak about with you later. But to sum up, I find this result very interesting, and it should be animating research questions in this field. Okay, physical processes. So now I'm going to focus on the North American monsoon, just as how David spoke about it in the morning. So this is the northern phenomena that develops over the Sierra Madre Occidental and it extends into southwestern United States. And it has recently been proposed, again, to the point of how the underlying theories of monsoon systems are still evolving. A physical mechanism that is quite different from what we are accustomed to when we're thinking of monsoon circulation. So Booth and Pascal argue on the basis of idealized modeling. So this is a numerical global model in which they did a realistic simulation and another one in which they eliminated topography over Mexico. And the results, they argue that the North American monsoon is, in fact, the signal of a standing orographic wave that arises from the easterly circulation, mid and subtropical easterly circulation, and its interaction with topography over Mexico. Besides this idea of large-scale orographic forcing for the monsoon, what I want to put a focus now in the next few minutes is processes that occur essentially in the region of the Gulf of California. And with the caveat or with the asterisk of saying that these are not necessarily mutually exclusive. So I'm not saying that it's either this, that the monsoon is just an orographic wave, or this other idea, which is more related to classical monsoon thinking, in as much as we understand monsoons as being some sort of thermally direct circulation of airflow from the cool, moist ocean waters flowing over into the continent. Okay, so either way, it's a clearly recognized feature of the North American monsoon is the seasonally reversing airflow near the surface over the Gulf of California. And we found a result some time ago that this airflow, near surface airflow, correlates very well with air pressure differences in the region of Mexicali. So this is the region of a thermal low. The Imperial Valley is just to the north of this. So regions with the highest temperatures on planet Earth during summers, no? And the cool, moist air in the southern Gulf of California. So these pressure differences correlated against the moisture fluxes, near surface moisture fluxes, indicates or is consistent with us having what is happening here is a channel-like flow, and you have, obviously has to be ageostrophic because this flow then is crossing isobars, which is something that you can't have if the balance were geostrophic. We're in the boundary layer, so to begin with, we don't expect it to be geostrophic flow. But what we have then is something akin to a land-sea thermal contrast, right? So if this is warmer and the water south of the Gulf of California is cooler, then we have a greater gradient and more moisture flux into the Gulf of California. So this is essentially one mechanism that we have been thinking about for some time that would be responsible for at least some part of the interannual variability of the monsoon. And I guess what normally happens to me is that I spoke too slowly in the first, and I'm going to have to hurry up at the second half. Am I with 10 minutes or 15 minutes left? Okay. Yeah, so adding to this idea of what is happening in the Gulf of California region that is important to the North American monsoon. Well, one thing that has always been interesting for us, I didn't mention where I work at the beginning of the talk. I come from the Physical Oceanography department at CICESE, so obviously we've always had a keen interest of understanding how oceanographic and meteorological processes intertwine. The Gulf of California has historically been a major subject of scientific interest for my research institute. And this feature here is, I would argue, a very interesting feature for regional studies. This is the SST contrast between the Gulf of California and the cool California current waters that ocean circulation in this region goes from the pole towards the equator. And so this SST contrast can be as high as 10 degrees centigrade, which is a tremendous SST contrast. It probably won't find another region on the planet where you have such large bodies of water with such different sea surface temperatures. And what does this SST contrast do to the near surface circulation? It produces a region of very interesting breeze circulation. So over the peninsula of Baja California, we don't just have the afternoon breezes flowing from the Pacific Ocean and from the Gulf of California over the peninsula and triggering a little bit of convection. I was interested to hear David speak about this in the morning. Obviously, this is a very different context than what he was referring to when he mentioned that breeze systems triggering convection. Here we are in a completely semi-arid region. Notwithstanding that, the fact that we have daily clashes of breezes from opposing coastlines, and we still have a very dry peninsula, I think in and of itself is an interesting question. Why, if we have this like daily motor clashing air masses, don't we have a consistent rain band over the peninsula like we do over other peninsulas like Florida, which is much more humid? Anyway, that's another question. The important thing to see here is, as is shown in this WRF simulation, that the flow characteristics of the breeze that respond over the Baja California Peninsula have this afternoon clashing of breezes, but then a second breeze system at night that would be related to the SST difference, which is maintained throughout the diurnal cycle. So during the day, you have lower pressures over the peninsula because of insolation, but at night, when that relaxes, what takes over is the pressure differences due to the cool California water and the warm Gulf of California SST. So keep in mind this result. We have these breezes, these rigorous breezes over the Gulf of California region. We also have, I guess this is an interesting, it ties very well with this morning talks. Adrian was talking about capping inversions and how they play a role into developing or inhibiting convection depending on the situation. The North American monsoon experiment in 2004, among other things, gave us this grid of radiozones before in mid-June. So this is before the onset of deep convection in the Sierra Madre Occidental, and then mid-August when convection is fully developed. And these are the mean temperature profiles from radiozones that were launched at sea, which makes this a very special data set. And on this side, we have the corresponding profile of relative humidity. So the dark line is the mean, in the gray is the spread of the data set. And in early June, when the Gulf of California is still not completely warm, when this SST contrast that I was talking about hasn't yet developed, we have the capping inversion, but and that dry atmosphere in the boundary layer and above, or just above the surface layer. But a few weeks later, when convection is well developed to the Sierra Madre Occidental, we have a very much more moistened atmosphere, and the inversion has been eroded, presumably due to the energy coming from below. The Gulf of California in these interceding weeks warmed up to almost 30 degrees Celsius, which gave the energy to erode this inversion. Okay, so how would this play into the monsoon dynamics? Here we did some simulations with a WRF model that I believe captures this very well. So before onset, you can see the inversion here by the changing color scheme. The colors, no? You can see that. And these are the panels. Let me get my bearing here. Yeah, this is before onset and then after onset. And these are the corresponding mixing ratio, water mixing ratio panels, no? So before deep convection develops, you have the thermal inversion, and not a very moist atmosphere. But a few weeks later, the thermal inversion is gone, and now we have a lot of moisture that clearly is flowing from or is being transported from the Gulf of California into the regions where it would feed into deep convection over the Sierra Madre Occidental. Okay, so all of this is to argue that low-level transport over the Gulf of California is an important source of variability for the monsoon. Here, the point is illustrated comparing composites from a product that is maybe now come out of use, but it was very useful 15 years ago, the North American Regional Reanalysis. And so we're seeing cross sections over the southern Gulf of California of this is moisture flux going into the north, and these are composites for active monsoons or wet monsoons, and the average monsoon, and for monsoon seasons that were dry, that almost didn't dry. So you have an almost twofold increase in the moisture transport over the Gulf of California. I think I'm going to speed up a little bit here, just to have time to cover another subject. So Juan Carlos Reyes, in his thesis, he looked at how this moisture transport over the Gulf of California correlates to the ENSO phenomenon. And he found a very interesting thing, that the relation appears to be changing over time. So this is a correlation map of an index that measures moisture convergence over this region of the Gulf of California, and correlating against sea surface temperature in the Pacific and Atlantic. And if he does the exercise for this 30-year period, 1979-2006, so this means he gets one SST value for each season and one moisture flux conversion value for the corresponding season, and correlates it. And he does this over a 30-year period. The influence of ENSO is clearly suggested by the arrangement of the correlation maps. He repeated the exercise, but now moving the time period of analysis closer in time to current date. And very interestingly, the relation pretty much disappeared. So again, this gives an argument that the processes that control the monsoons on an interannual time scale are not fixed, are dynamic, are complex, and in fact, there is much to be learned from them still. I will finish the talk now just making a few points about another feature that David brought up in his talk that he mentioned is very important to the development of the monsoon circulation. So in the upper troposphere, we have this anticyclonic circulation that progresses as the season evolves, more or less following the axis of the Sierra Madre Occidental. This is also done with the NAR data set, and these are 500 millibar climatology of horizontal winds. And you can see that the anticyclone on a climatological time scale is a very well-defined feature of the atmospheric circulation in this region. Now, if we look at trying to look for this anticyclone, but not from the point of view of time mean climatological quantities, but looking rather at something more instantaneous, as can be done with using the ERA 5 data set and then using this other variable, which hasn't been mentioned, but is very important for atmospheric dynamics, the variable of potential vorticity. Here we're looking at one single value of potential vorticity mapped onto a surface of constant potential temperature. This is a cross-section of potential temperature from ERA 5 that corresponds to the time when we're seeing this evolution on this solar panel. So here we can see that the anticyclone has the effect of producing a suppression in the isotherms of potential temperature. And we're looking at potential vorticity mapped onto this surface of 340 K potential temperature. And what it shows is also very interesting. No? So what the message here is, the anticyclone is not a coherent structure present throughout the entire monsoon season, but rather, as we would, I guess, expect, because obviously things up there are dynamic, we have the jet stream just north of here that is constantly evolving as Rossby waves that turn into vortices and inverted troughs, etc. We can see then that in the course of 1 month, the anticyclonic circulation forms clearly in the latter half of the month, but here the animation will return to the first days of July, and you can see that you will be able to see that it was not the case at the beginning of the month. Now here you can clearly see the anticyclone, but give it a little bit more. I guess it didn't return to 1st July. Well, anyway, here you can see there, no? At another point of the month, the circulation was disorganized and the anticyclone was not formed as a coherent structure. So this represents a whole different set of physics that probably plays into the interannual variability of the monsoon. How and why does the anticyclone form? When it is well formed, it is, among other things, what it's doing is shielding from the rest of the circulation outside of this region. Obviously is westerly, no? And when the anticyclone is well formed, then you have a more convenient environment for deep convection and for moisture to be retained in this region. In the absence of this anticyclonic circulation, the moisture would quickly be transported out eastward of this. No? Okay. So to illustrate the point, these are composites for circulation for when years with active monsoon and plenty of rainfall, and you have a more northward developed anticyclone in the composite, in the mean, and when you have weak monsoon and dry conditions over the Sierra Madre Occidental, the anticyclone is less extended, is southward displaced. Okay, now, so I promise this is the end, but I would want to get to this point and not say this, talk about this. So Christopher Castro published this paper in 2005, and giving this very interesting, intriguing result, which is a composite of geopotential heights made on the ENSO phenomenon. So these are geopotential heights averaged for over a month, and then he's including in one group the El Niño years, and in another group the La Niña years. And what we see is the difference between both, Niño menos Niña. And here, what forms is a very interesting pattern that suggests a zonal propagation in mid-latitudes at a time scale that would indicate the action of stationary or close to stationary Rossby waves. There is a tool to study Rossby waves and in their interaction with time-varying flow, which is the wave activity flux. I had some comments to make about this because this is also an important tool from dynamics to study the dynamics of the atmosphere. It developed studying the zonal average of the atmosphere, so more the Elias and Palm fluxes were developed to study more in the meridional plane and waves, the effect of waves transferring information from the tropics to the higher latitudes. But here I missed a little bit here of equations, but Nakamura is a scientist that has developed for many years this theory and overcoming the formulation of wave activity flux for zonal averages to include it for a 3D time-varying flow. And here we have an example of how Yadav recently used this tool to illustrate how Rossby waves probably in an analogous manner as how we're arguing that happens for the North American monsoon, modulate the Asian monsoon propagating over Asia. So what I should say is that if you're not familiar with this, wave activity is a quantity that is related to the momentum and the energy of a wave propagating on a flow, and its flux is used, more specifically, the divergence of its flux is used to ascertain sources and sinks of waves propagating on flows. So these arrows here are arrows of W, which is the flux of wave activity. And Miriel Tapia, who's about to finish her master's degree in a few weeks, produced these very interesting results for El Niño and La Niña over the North Pacific Basin. And so what the conclusion here is that, yes, what is suggested by Christopher Castro's figure that Rossby waves with very low frequency propagating over the Pacific probably play a role with the North American monsoon, because this wave activity gets to the region where the anticyclone is evolving, right? I guess now I'm on time. It's time to finish. Yeah. Okay, so I will just finish with reading a list of questions that I hope are of interest to you. So we have this interesting, important suggestion or proposal that the North American monsoon is not really related to land-sea thermal contrast or thermally direct circulations, but rather is a feature of orography interacting with low frequency circulation. But as I showed in my presentation, we also have plenty of evidence that thermal forcing, at least in the lower atmosphere over the region of the Gulf of California, also plays a role. So an interesting question to answer is, or to address, is which of the two on the interannual scale is stronger or more important? Which other physical mechanisms are involved in the ENSO-NAM-TEDE connection besides this low frequency Rossby wave that I just showed? What should we do with results of global models that don't see the Gulf of California? If we want to extract from them any type of conclusion about how the climate will change in the future. If they don't see the Gulf of California, none of what I was talking about is represented in those models. So if the result is the future North American monsoon is going to dry up, the question will be, well, but you don't do it, no? What about these other processes? I would argue that there's a whole list of opportunities to put the focus on an upper level anticyclone and study all the physics regarding its evolution. There's another set of tools that corresponding to Lagrangian methods and what is derived from dynamical systems. These manners of objectively placing the boundary of coherent structures in flow, which I think can be used to study the evolution, formation, dissipation of the anticyclone and how it plays into the context of the North American monsoon interannual variability. And I didn't speak about inverted troughs, but I know Christian is going to speak about this later in the week, so maybe it's good that she's going to have a talk on this, but this is a whole different mechanism that is introducing variability into the region. These upper level vortices that propagate over the Sierra Madre Occidental and produce different type of convection environments. So that is all for me. Thank you.
Questions? Sure. We had Bill Booz here. Oh, I'm sorry. Oh, let me make a nasty comment about Bill. So Bill was here. Yeah, I mentioned actually very similar points to what you were talking. Like I told him, eliminate the Baja California and see if you still get the same result. We have the cold Pacific water coming all the way down. So he doesn't talk to me anymore. That's a joke. He talks to me. All right, go ahead.
A couple of questions along those lines. So it would be, so I studied the North American monsoon earlier in my career, and then I started looking at larger scale monsoons. And I think that what makes the North American monsoon really interesting is how varied the orography, the geography of the area is. And I don't know if that was part of the things that you skipped, but you were showing maybe some results from WRF. And again, along the same comments as they was making, have you tried to maybe run some simulations where SSTs over the Gulf of California are made exactly the same as the ones, so varying meridionally as they do west of Baja? Or have you tried to run simulations where you fill the Gulf of California with land, and how would the North American monsoon be different if that were the case?
Yeah.
In the sense that these are things that I thought a long time ago about doing, but then never did. And I don't think there are similar studies that exist in the literature at all. And I think it would really be a neat way to test some of the hypotheses that you are discussing here.
Yes, actually we did. We are finishing up a project that did something similar to what you're saying. We didn't go as far as to fill up the whole of Gulf of California, but we did. Let me see if I got this here. Yeah. So we did different mesh resolutions for WRF from 4 kilometers, which is clearly resolves everything that I mentioned here, all this breeze systems and all of that. And then with intermediate resolutions all the way to 90 kilometers, which approximates the resolution of global models, and that pretty much only barely sees the Gulf of California. And an interesting result about this is, so these are moisture flux along this direction. So zonal, this is a cross section over the Gulf of California at 25 or 26 north, something like that. So this is Baja California, this is the Sierra Madre Occidental, and this is the zonal moisture flux in the direction, in this direction, right? So And these are results before convection onset and after convection onset. And it is interesting to see how this would be the component of the moisture flux that we could think is attributed to a coupling of the sea breeze with the mountain breezes. And so an important way of how moisture gets from the Gulf of California to the upper reaches of the Sierra Madre Occidental. And this exact same situation in a model that just barely sees the Gulf has very weaker moisture transport. So I guess sort of arguing that these are in fact important processes.
If I can, I have another question. It
Yeah.
was very nice. I really enjoyed your animation of the upper level anticyclone. And that reminded me very a simple study that Sue and Plum did, I think in the early 2000s on a shallow water model, talking about how an anticyclone breaks down in eddies and sheds eddies. And so I was wondering if you've looked a little bit better at the dynamics of this once the anticyclone is well established, again, how this filaments and how it evolves, and if there is any interesting connection with, for instance, monsoonal precipitation and other things.
So not really. Haven't done that work, but that's exactly the things that I'm thinking that are interesting processes to study. Yeah, thank you. Okay.
Thanks, Temo. Oh, question? Okay.
Thank you so much for the presentation. I'm really interested in this phenomenon. According to the latest ENSO release, we're facing neutral condition at the end of this year. So I was wondering if there is any research of correlation when we face neutral conditions instead of La Niña or El Niño in Mexico.
So no, I don't have a map or a result to specifically for neutral years, no. But I guess the only thing that I can point to is just the fact that although I argued that El Niño is the major driver of interannual variability here, it still does remain, the fact does remain that the correlations are weak. It's not, I guess it's hard, it's a hard question to answer, what I'm saying. Not very clear what takes over during neutral, what processes take over during neutral years that would give an answer to what you're asking. But in this right now, currently we are in a niña state, right? A weak niña, yeah. But you say it's forecast to dissipate in the next few months. Yes. Yes. Thank you.
Okay. All right. Thanks, Temo. Next speaker. Spencer. Spencer is also from California, so he speaks English correctly, unlike other people.
Yeah, now? Yeah, I hear it now. Great. Yes, I was born in California. When I was 7 years old, we moved to Kansas in the middle of the country, so it's partial. Yes. Okay, great. And the slides are up. Zoom's okay, I trust. So we just go for it. Okay. All right. Buenas tardes. Good afternoon, everyone. It's really a pleasure to be here, and thanks for sticking it out to this last in a real series of lectures, a long day. I'll try my best not to keep us any past the 5 o'clock hour. And yeah, you could think of this as sort of bookending along with Simonos to start from a very theoretical place, this intro first dive into monsoons for the week. I'm going to be returning to that after a bit more phenomenological perspectives from David and Cuauhtemoc. And trying to answer sort of in the simplest possible terms, the most fundamental building blocks, what is the tropical general circulation and why does it occur? And take the general form that it does using the simplest possible equations, arguments, etc. First, though, I wanted to share, great, a little about the university I come from, the City College of New York. It's one that isn't exactly well known on the international stage, frankly, not even outside of the 5 boroughs of New York City. But it's a very cool place, a very cool history with connections to UNAM, or analogies to UNAM, let's say. So it was founded in 1847. It was called the Free Academy. And it was an experiment. It was the United States' first free public university. And a quote here from one of the founders, the question was whether the children of the people, of the whole people, can be educated, and whether an institution of the highest grade can be successfully controlled by the popular will, not by the privileged few. And I was reading a little bit about the history of UNAM. You can imagine I saw some parallels there. Oops, that's forwards. We are no longer free, truly, but we are still very affordable. And so it is a predominantly working class. It always has been student body, often referred to affectionately as the poor man's Harvard. And we are officially an R2. We are officially a minority serving institution and a Hispanic serving institution, which are classifications within the United States that, yeah. And then it's very confusing. CCNY, the City College of New York, is one university. There are 24 other universities or colleges within the City University of New York system, which was founded in the late 60s. So CUNY is the bigger thing, and CCNY is this thing within CUNY. We like to think of ourselves as the crown jewel. And then the very last thing, I was just on the Wikipedia of UNAM wanting to learn more. Forgive the small text here, but I learned of the 1968, maybe not even on this paragraph, the 1968 student protests here that were sort of a real watershed moment in student organizing. Surely, I don't know this for a fact, but in 1969, one of CCNY's big historic moments was called the 5 Demands, where students sort of took control of the entire campus, locked it down for several days in demand of better outcomes with respect to racial equality and other things. And I can't help but imagine they were strongly influenced by the UNAM folks in '68. I'm not that fiery of a progressive in general. Don't get me, to be honest. I'm pretty much a centrist, but still, I really appreciated this history. Okay, now to the science. I'm going to force you guys to interact a little bit more here than we've been doing. And we'll do what's called a think, pair, share. I'm going to pose to you this question. I want you to take a few seconds to think about it, and either continue thinking about it with yourself, you can jot notes to yourself, or turn to someone near you and discuss. This thing, the general circulation that we're about to talk about for a long time coming, what is that? If you don't know what it is, what might it sound, what might it be? Okay, so go. And I'm going to call on somebody. Somebody has to volunteer. We'll see if someone volunteers. Yeah. Usually we get someone. Then you just pick one. Yeah, at random. Oh. All right. Let's start to bring it in. All right. Where's our volunteer? Who wants to take a gander at this one? The general circulation. There we go.
Yeah. Well, so I was saying that probably the first thing that comes to your mind talking about general circulation is the Hadley cell, and probably use like a thermal driven circulation. Just because you have the equator warmer than the poles, then you will have rising air at the equator and subsiding, just like fiercely thinking at the poles, just by thermal stuff.
Great. Yeah. Okay. That's great. So we've got the specific phenomenology of the Hadley cells. We've got the insulation gradient. We've got a lot of ingredients there. Yeah. Nice. For the sake of time, I'm just going to keep going. And well, for the sake of time, I'm going to turn to a true expert, which would be our ascendant AI overlord, ChatGPT, right? So I asked it, I think this was the 4.0 model, one sentence, what is the general circulation? And it nailed it, right? So quoting, the general circulation is the large-scale global pattern of atmospheric motion that redistributes heat, moisture, and momentum across the Earth, driven by differential solar heating and the planet's rotation. Okay? So it's the flows within the atmosphere at the largest scales we can possibly describe them usefully that generate these movements of moisture and heat and momentum that set the time mean distributions of those fields, put it that way. So by time mean, what we mean is simply a long-term average, and an analogy or a synonym for that is a climatology. A climatology is the long-term average in our field. Zonal mean, we go from the individual monsoons. So briefly, Cuauhtemoc had a slide showing the 6 individual monsoon regions, right? North American, South American, West African, Indian, et cetera, et cetera. You zonally average, you average across all longitudes at each latitude. Within the tropics, those become, instead of the individual monsoons, you're left with these overturning Hadley cells, and the ascent and rainfall part becomes this intertropical convergence zone. Monsoons are inherently seasonal, right? We're in the dry season right now for the NAM. The time mean doesn't always mean you're averaging over all months. You can take the climatology of an individual season or month, right? And so the climatological seasonal cycle, i.e. the monsoons, is part of this general circulation that we're trying to understand. If they weren't, we wouldn't be talking about it in the monsoons workshop. Nonetheless, we're going to start with the annual mean picture and then come back to the seasonal cycle in the second part, just because it's easier. Okay, next question. This one you'll just think about to yourself. What, if the general circulation was what ChatGPT just told us, what then is the tropical general circulation specifically in the title of my talk, which was given to me? It's a trick question. It's just the part of the general circulation that's in the tropics. Okay, so we really want to understand, if I go back to the schematic, we really want to understand this stuff because that's where the monsoons are. There are crucial interactions with the higher latitudes, but we're going to understand those only insofar as we need to understand the tropics. Okay, so our starting place actually is a concept that Adrian brought up called radiative convective equilibrium, RCE. Okay, the RCE state is one that emerges in proper conditions at sufficiently large horizontal scales. So think a 1,000-kilometer box, say, in which in the time mean there is a balance between the forcing, so the combination of the insolation, your boundary fluxes through the lower surface, as well as your radiative fluxes out through long wave radiation. Those balance the fluxes through convection. So here's an example from normally a climate model, so on the sphere with rotation and everything, but they've turned it into just a homogeneous, doubly periodic box. So this is just a snapshot of precip. So blue is no precip, red is very high precip, and this edge wraps around to this edge wraps around to this edge, and the whole bottom boundary is uniform sea surface temperatures, the insolation is uniform. So the whole thing is uniform. And this is just a snapshot at a particular time. You see convection and heavy rain sort of spread about the domain in certain points, popcorn convection sometimes called, and sort of subsidence dryness everywhere else. This is from a 2007 paper led by Isaac Held. So at any given time, such as this one, as I just said, some locations are raining, others are subsiding. But if you took an average over this whole domain, over this snapshot and then many others afterwards, you would get this balance that I mentioned before. The ascent from the convection, there's less area, but it's faster compared to the broader but slower subsidence. So among other balances, the vertical velocity of the whole domain is 0, right? And that makes sense because you couldn't have a time mean vertical velocity of the whole domain. The whole domain isn't slowly lifting into the sky, right? People have done similar things. That was with a climate model, so parameterized convection, things like that. More recently, in a paper by Ali Wing, you have many different cloud resolving models did this same setup. You get a similar phenomenon. As long as it doesn't aggregate, Adrian sort of alluded to that as well. I'm going to sidestep convective aggregation entirely. And now we're getting closer to the real Earth. You can actually get this state on a spherical Earth instead of a doubly periodic domain. This is from that same Ali Wing paper. Provided that, again, you make the forcing at TOA, top of atmosphere, and the lower boundary completely homogeneous, and you make the system not rotating. If you do that, you get a whole Earth full of just this popcorn convection. So Adrian nicely brought up Minami and Weatherald, sort of perhaps the seminal paper of our field, if you had to pick one. It was the paper that underlied Suki Minabe winning the Nobel Prize, the first ever for climate science, actually. The net result of this popcorn convection and the compensating subsidence, et cetera, is an upward transport of heat and moisture from the near surface to higher up in the troposphere. Gives you this moist adiabatic lapse rate, which Simona nicely derived as well. And yes, the curves to focus on here are, this dashed one are the, this solid one is the pure radiative equilibrium. So if there was no convection, and you get this incredibly steep drop off of temperature with height immediately below the surface. And the radiative convective equilibrium solution here, this dotted one, you instead get this much flatter lapse rate, a much warmer upper troposphere, a cooler surface. So at any given time and at any given location in these situations, in simulations like this one, for example, you have motion, right? U, the zonal wind is something, it's not zero. V, generally, the meridional wind is not zero. W, the vertical velocity in general is not zero. But if we use an overbar to denote this time mean, domain mean, all of these fields are zero. There's no large scale net motion, which is a fun property of that of an RCE system. But for monsoons, it's bad news because monsoons are a vigorous, especially, well, all three of these are strong, right? You have a monsoon is a meridional overturning circulation, right? But the question is, why aren't we in the RCE state compared to the actual world we're in that does have monsoons and all these other features in the tropics? So even if we took out the continents, we lost the NAM, which would be sad, but if we were just an aquaplanet, no zonal asymmetries whatsoever, we took out the seasonal cycle, we took out the diurnal cycle, the time invariant, there would still be two key ways in which that resulting system would differ from these previous RCE systems that we just saw. So what are they? It's usually a good idea. I mean that, I actually mean that literally, to ask GPT. Let's recall what it told us. Just reread this to yourself maybe. So to yourself, pick at least one thing that's important here that's different than the RCE case. And what is it? One, the insolation is not uniform, right? We actually heard already. And two, the planet is spinning. So we're going to work through each of those in turn and what they do, and then in combination what they do. Okay, so non-uniform insolation. This, most of my figures, as much as possible, I just try to take from Wikipedia. This is annual mean insolation in the color shading. You can see the continents sort of crudely outlined in the green, going from 0 in the purple to above 400 watts per meter squared in the yellow. And we have this very strong gradient, right? So we have 400 watts per meter squared or so in much of the deep tropics, down to less than half of that, a third of that or so in the high latitudes. And that's easy. Earth is a sphere. The sunlight's all coming at the same angle. So at the equator, it's a flat, you're hitting it dead on. At the pole, the surface, you're just barely glancing it, right? So there's less photons hitting each square meter of surface. The state that would emerge if each latitude was in RCE, i.e. if there was no general circulation, given that insolation gradient, that RCE state would also have resulting temperature gradients, right? So I've shown that here explicitly in a paper with Simona and Jonathan Mitchell in 2020. we did these numerical simulations of RCE on a latitude by latitude basis, and then just kind of concatenated them together. And the key here is just the green is sort of a troposphere averaged temperature at each latitude. And you see this strong meridional curvature, right? Highest at the equator, decreases monotonically towards either pole. Okay, so just sort of stow that away in your mind for now. Non-zero meridional temperature gradients. Okay, next, the planet is rapidly rotating. Again, a Wikipedia schematic. So relative to the orbit, our rotation axis is tilted. That matters for the seasons, but for right now, what especially matters is that that rotation is non-zero and is rapid enough. Our once per 24 hours revolution is rapid enough to be that we would consider our planetary body to be called rapidly rotating, where the rotational effects play first order influences on the large scale flows. This is pretty much the rotation always is able to be encapsulated into the Coriolis parameter F, and that's just twice the rotation rate itself times the sign of latitude. So this phi symbol is latitude. The sign of latitude part is simply because we won't go into it, but what matters regarding the rotation is the rotation in the horizontal plane, right? Not the vertical. So if you're standing on the pole, the world is spinning around with you, right? So it's spinning horizontally. If you're standing on the equator, you're sort of more getting spun, you know, pretend this is my face. If I'm at the equator and spinning this way, there's that type of rotation, but there's not horizontal spinning. So if I had a globe, I use a globe and a Lego figurine that I tape on there, and it's really clear. At any rate, yeah, for the sake of large-scale atmospheric dynamics, at the equator, it's essentially it's non-rotating. Right, so this is of fundamental importance, this rotation and its gradients. Sort of one way of thinking about this is that as the parcels of air are rotating with the Earth, we are in a non-inertial reference frame, right? So recall from physics, all the laws of physics are sort of take an inertial reference frame, a non-accelerating frame. As such, there are these sort of apparent forces that emerges from the rotation. And again, we encapsulate that into this Coriolis parameter thing, F. Just to show that explicitly, start with the first top half of this slide, showing you a simple horizontal momentum equation. I should say the horizontal momentum equation for a simple fluid system. This was just a single layer, inviscid, non-rotating fluid. This bold U is the horizontal wind vector, so U and V. And it's a very simple equation. We have a local time tendency, and this is just an advection. This left-hand side in total is the material derivative. It's just the change of the velocity as you're flowing with the fluid itself. And the right side is just the pressure gradient force. So the nabla P is the pressure gradient. The rotating case, all that happens is you add in this term here on the left-hand side. So it's the cross product of the Coriolis term with that horizontal motion. So you might recall from your calculus class that any cross product, the result of that cross product is perpendicular to both of the things that were crossed with one another, right? So it will be at a right angle to F, but more importantly, it will be at a right angle to the flow itself. What does that do? It causes, in short, it causes flow to be approximately geostrophic, we call it, which means that rather than flowing down the pressure gradient. So if we weren't rotating, this H is for high pressure, L is for low pressure. If this was a fluid that was not rotating, high pressure to low pressure, there would just be direct flow from the high to the low, right? The rotating system, the flow wants to go there, but Coriolis turns it at a right angle. And a geostrophically balanced state is when those are perfectly balancing each other. And when that happens, the flow goes not across lines of constant pressure of isobars, but it follows them exactly. Your isobars, your constant pressure lines tell you exactly where your flow is going. Okay, so that's geostrophic balance is a single fluid layer. We are in a thin shell atmosphere, but we still need to consider more than one single layer to understand the system. So we want to look at how the flows are changing vertically in the next step here. In a system that's reasonably geostrophic, the way of doing that is invoking what's called the thermal wind relation, where basically you're just taking the vertical derivative of the geostrophic flow. And before I was putting it all in terms of, excuse me, the full UV vector. Right now, we're going to shift. It's the zonal flow that we're really interested in right now. So the zonal component of thermal wind tells you that the vertical shear of the zonal wind, meaning its change with height, is proportional to the meridional temperature gradient. Okay, so stronger meridional temperature gradient, stronger vertical shear, change of your zonal wind with height. In the northern hemisphere, the Coriolis parameter is positive. Well, the annual mean, I think I missed a minus sign here. So I think there should be a minus sign here and a minus sign here. So that works out though. The point is that sorry for that, but this term for sure, du dz, is positive. As you go up, the flow is becoming more eastward, more westerly. In southern hemisphere, both the Coriolis and the temperature gradient signs get flipped. And so negative, negative, same thing. So everywhere you get this in the case of this annual mean case where temperatures are decreasing monotonically towards either pole. Okay, so at the surface, we have friction. So air directly at a surface can't go through it, and so its motion goes to 0. We have, that's called a no-slip boundary condition. So if the zonal flow is 0 at the surface and it becomes more positive going up, and that is true at all latitudes, that means that within the atmosphere, your zonal wind is positive going eastward at all latitudes. So everywhere over the whole domain. And here, I just wanted to emphasize with this RCE subscript, if you've lost the thread, all of this is we're thinking about this hypothetical case. What if there was no general circulation? What would the system look like if we were just everywhere in this local radiative convective equilibrium? To get a better sense of that, you can look at just the blue curve, just ignore all the other elements here. And there's no labels, sorry. This is South Pole, Equator, North Pole. A different paper with Simona and Jonathan. Maybe it was the same one. We had several. The blue solid curve is basically this RCE zonal wind in the lat by lat RCE case. At the tropopause, sort of at the top of the weather layer. And again, you see this, it's positive everywhere, right? So here's the 0 line. There are no easterlies, right? It's positive at the equator, which is itself important, and it's a positive at all latitudes. Okay, so who cares? Sure, the zonal wind is positive everywhere. What's the problem with that? one reason that's I think the most fun, which is why I picked it, is basically if your wind is the same direction everywhere, right? So the Earth is rotating this way, and the wind, so say my fist is the Earth, it's rotating this way, and the wind everywhere is also blowing it that way, right? If you have something on a pencil and you blow on it one direction, it will start spinning, right? So if the wind is blowing the planet the same direction everywhere, it will spin up the planet, right? So if this were to occur, you would be, the planetary rotation rate itself would keep spinning up, right? And keep in mind, this is a steady state time average thing. So if you have an acceleration in your time average, then that's a runaway state, right? Clearly, Earth's rotation rate is not rapidly sort of running away. And so instead, what you end up with is, the plot didn't make it on here, I should have, but if you look at a plot of the true surface wind, this is the upper troposphere, but suffice it to say there are regions where the surface winds are westerly, but then there are compensating regions, mostly in the tropics, where it's easterly. And so the stress averaged over the whole surface is 0. Oh, did I? Oh, yes. Dare we go back? Let's go for it. Yeah, perfect. So the white, thank you, Simona. The white arrows here signify the surface winds, right? And the trade winds, the tropical surface winds, all have this easterly component. The higher latitudes, it's more this westerly component. Thank you, Simona. Simona was my postdoc advisor at now quite a few years ago. And it's been a great collaboration ever since. And she corrects my mistakes from time to time, which I'm grateful for. Okay, so there are other arguments you can make specifically about the value at the equator, but I won't go into them for the sake of time. Hopefully I've convinced you that some circulation must arise. The question then is, what controls the form that circulation takes? How big is it? How vigorous is it, et cetera? So to think about that, we're going to recall two things from earlier slides. We have, and just surely you know that the insolation is highest at the equator, lowest at the poles. And from earlier on in the day, mostly from Adrian, we saw this convection driven by sort of heating near the lower boundary, right? You put those together, it's very straightforward that the convection is mostly going to occur at the equator, right? That's where the surface is being heated the most by the insolation. So given that, why don't we just have these global Hadley cells, right? Could it be the case that the ascent is at the equator, as in the schematic, and then the flow turns poleward, and in the upper troposphere just goes all the way to the North Pole, and then comes back again, and likewise in the southern hemisphere? If the Earth was not rotating, that actually would be the solution, right? There's nothing keeping it from doing that. But I just gave away the answer. The rotation is what prevents that from being the case. And to think about that more formally, we'll introduce absolute angular momentum, denoted with this capital M. So recall from physics class, angular momentum in general is simply your distance from the rotation axis times your linear velocity tangential to that rotation axis. On the Earth, if we use A for planetary radius, and again, phi is latitude, the distance from the rotation axis, so where this point is here, is A times the cosine of that latitude. So that's your moment arm, your distance from the rotation axis. Now for the velocity, we have two contributions, right? The second one, the flow itself, is straightforward. If the air is moving to the east, then it's spinning, there's an angular momentum associated with that. And then there's the planetary rotation. So the rotation rate times, again, this moment arm gives you the planetary contribution. So you just end up with this simple expression. So if the angular momentum, you have the distance from the rotation rate, that's this term, the planetary flow, so to quote unquote, and the actual flow. Okay, so we're at the equator. A parcel has been heated and lifted out of the boundary layer, and it enters then the free troposphere, right? So Adrian nicely covered more of the dynamics of the boundary layer. The key feature for our purposes of the free troposphere is that it is essentially inviscid. There's essentially no friction to speak of, because you're far away from the boundary, and molecular scale stuff doesn't matter for large scale for the atmosphere. Necessarily, inviscid means that your angular momentum value is not going to be changed. There's nothing that can change it. So a parcel leaving the boundary layer at the equator is essentially stuck with whatever angular momentum value it had. And moreover, that angular momentum value is the planetary angular momentum value, right? Because we've said at the surface that U is essentially 0, right? Okay, so it keeps its angular momentum value, but it's also flowing poleward. So let's say out here it ascends, it's moving poleward, and in so doing, it's getting closer to the rotation axis. So how is that, how to make both of those work? You're getting closer to the rotation axis, which would act to bring down your angular momentum, all else equal, but we've also said that the angular momentum itself is conserved. The answer, for sake of time, is simply that the zonal wind, the flow of the flow itself, accelerates to compensate for getting closer to the rotation axis. Exercise to the viewer, you can derive the zonal wind field that is this exactly angular momentum conserving field, or AMC, which is this expression here. It varies with the square of the sine of latitude with the cosine at the bottom. You can see here actual values. And the thing to point out, one thing to point out is it's very fast, right? So before you've even gotten to 30 south, 30 north, the boundaries of the tropics, roughly speaking, you're talking about speeds of excess of 100 meters per second. Extremely fast, much faster than the actual observed one. But it's a very useful starting point theoretically for us. This field cannot extend all the way to the pole, right? Forgive me. The cosine of latitude is in the denominator. Cosine of the pole is 0. It blows up. So that alone tells you that we can't have this global Hadley cell, right? And in fact, it turns out that the Hadley circulation can't go much beyond this 30 south and north sort of markers that we observe, sort of any way you shake the system. So there are two ways I want to highlight, but I won't go into detail on. The first is what's called the equal area argument from this classic Held and Howe 1980 paper. If the whole system was zonally symmetric, no zonal variations whatsoever, in that case, you have this angular momentum conserving wind, and what turns out to be the binding constraint on the extent of the Hadley cells is how much energy they are transporting out of the deep tropics and depositing into the subtropics. The equal area name comes from this dashed parts being the same area in this schematic from that paper. In Earth's real atmosphere, things are zonally varying. So here we are down here somewhere, right? Here's a satellite snapshot. You see one of these classic wintertime baroclinic eddies, okay, covering most of North America. And these are ubiquitous throughout the subtropics and higher latitudes. Again, glossing over the details entirely, and again, another Isaac paper, but suffice it to say that these eddies in aggregate come into the subtropics, they slow down the Hadley cell winds far below the angular momentum conserving value, and they just force the cell to sink in the subtropics as opposed to going any further than that. I'll come back to ideas we've built from this starting point later in the week at some point. Okay, so annual mean side, doing okay on time. Just super quick recap. We have an insolation gradient. We have a rapidly rotating spherical planet. We have a viscous boundary layer and a nearly inviscid free troposphere. Those give you an annual mean ITCZ at the equator. It gives you overturning Hadley cells descending roughly 30 south and north. It gives you westerlies in the upper troposphere within those Hadley cells. All things that roughly we actually exhibit in the real world. Okay, now finally, we will get to the seasonally varying part, which is sort of inextricable from monsoons, right? We'll start with the insolation. This is from Wikipedia. The seasonal cycle of insolation as a function of latitude is now on the y-axis, so South Pole, equator, North Pole, and in time in the x-axis. So ask yourself, it's this weird unit, but what is this time right here? Insolation, black means 0 insolation, yellow is highest. Black in the southern hemisphere, very high. In northern hemisphere, it's our summer, right? It's northern summer. Southern summer, spring, et cetera, et cetera. Insolation peaks on the equator directly at either equinox, so right here and right here. So two instants in time in the year, it is on equator, just like we were sort of thinking about it before. All other times, insolation is maximizing off the equator, right? And in the solstitial seasons, it goes all the way to either summer pole. So we'll return to this hypothetical lat by lat RCE state, but now in the seasonally varying context. And play the same game. Ask ourselves, what would emerge in that situation that is physically not possible? And that as general circulation then comes and takes care of. We explored this in a 2021 paper, Simona, Jonathan, and I. I'm showing you figures from that paper. Again, here we've done this numerical simulation of the lat by lat RCE state. And again, it's South Pole to North Pole on the x-axis. Sorry for the lack of labels. Just focus on the solid red as the actual simulation results. This is this tropospheric temperature. You see sort of monotonic nearly increase, and certainly through the deep tropics moving northward. So again, you have this strong non-zero temperature gradients. The corresponding winds that would be in thermal wind balance with that. You might recall in thermal wind, the Coriolis parameter is in the denominator on the right-hand side, and Coriolis goes to 0 at the equator, right? And so the thermally balanced, if there's any non-zero temperature gradient at the equator, your thermal wind blows up. It goes to plus or minus infinity on either side of the equator, right? And there's your answer for why a general circulation emerges right there, right? We can't have an infinite wind. So there has to be some sort of circulation that emerges, at least in some narrow vicinity within the near the equator, right? That somehow smooths that out, that gets us back into reasonable values. But again, the question is how far beyond that? Is this really only a few degrees within the, could it be just within a few degrees of the equator? Or conversely, the insolation maximizes at the summer pole. Could that ascent be all the way at the summer pole? Or somewhere in between? The easiest way to think about that is introducing a new quantity called absolute vorticity, eta, which is the sum of the Coriolis parameter, which a synonym for is planetary vorticity. And this new term, zeta, is the relative vorticity, which in this case is just minus now the change in the zonal wind with respect to latitude, du dy. Another way of thinking about the absolute vorticity is it tells you the gradient of the angular momentum itself. Okay, same simulations as the previous slides. These RCE lat by lat in the seasonally forced case. And maybe I didn't mention, in this case, it's northern hemisphere summer forcing, right? So the heating is max here and decreases to all the way to the South Pole. Just like the angular momentum is on the top, just like the zonal wind, it blows up one direction or the other in the direct vicinity of the equator. And then here's your absolute vorticity in the bottom panel here. The dashed is if there was no flow whatsoever. It's just the Coriolis term in that case. And you have this sort of straight line. What you get instead in the red is this field where you have the key to notice here is that rather than being positive in the entire northern hemisphere, like the dashed line is, you have this region from the equator to 15 or so degrees where it has changed sign, right? The red is negative, the dashed is positive. This region we call, following seminal papers by Plum and Howe and Carey Emanuel in the 90s, the supercritically forced region of the domain. And the sort of compact way of saying that is that the product of F and the absolute vorticity is negative. Again, there are multiple ways you can argue why this can't sustain in the time mean. And I'm just going to pick one that's sort of fun. And this comes back to Carey's paper. Basically, if you start from rest and you look at the vorticity equation, the equation governing how the absolute vorticity evolves in time, if you're at the tropopause where the ascent is 0, then when you hit eta equals 0, so you start with it positive, right? And then the question is, can you get it to change sign, right? When you hit eta equals 0, the time derivative itself goes to 0. And that means you're not changing in time, right? So you can't get across 0 because you get stuck, essentially, when you get to 0. And so if you can't get there, it's in an impossible state. And that means that the time mean instead has to have some sort of circulation that, again, smooths out these fields, gives you something that is physically realizable. All right. With apologies for slightly just parading Simona and my papers, in the next in this series of papers, what we did was use this. We came up with an analytical expression, an approximation for this supercritical forcing extent, and basically took an aquaplanet simplified GCM climate model and used that supercritical forcing extent to predict the seasonal cycle of the ITCZ of the sort of, this is a zonally symmetric force case. There's no individual monsoons, but you think of the zonal mean ITCZ as sort of the monsoonal rain belt of this system. And that's the key here in this. So going from December through November versus latitude, the contours are the Hadley cell basically at the 500 hectopascal level, the stream function. The red solid is the actual ascending edge. You can think of just as the ITCZ for our purposes. And the dashed red is our theory based on this tropical supercriticality for that field. Once we thought a little bit carefully about the lag because of the thermal inertia, that's what these other fields are, the stars. So does a pretty good job, at least in this simple aquaplanet. So we were very happy about that. Later in the week, I'll talk about extending that to the real world. And then for kicks, we also combined that with this theory I mentioned in the previously from Isaac's 2000 work, where you use this baroclinic instability arguments to tell you where the descending edge in the winter hemisphere should be. And again, the solid, now this is blue, solid is the full field, the dashed is our theory, and it does a pretty nice job. So, okay, well, good. I should just squeeze in. Maybe time for a question or two. Akin to the situation I mentioned earlier, this supercritical forcing extent is technically a lower bound. The circulation has to go that far, but why doesn't it go much further or not? And more generally, can we come up with something that gives you a precise value rather than a lower bound on where that ITCZ, the monsoonal ascent, is occurring? Again, here, in this case, I'm just gonna say their names. I'm not even gonna give you a overview beyond that, in part because we'll make sure to cover them in the coming lectures between Simona and I. One is basically just a seasonal extension of that equal area model I mentioned before. This was done by Linzen and Howe in 1988. And then more recently, since the 2000s, really, has been this energetic framework for the ITCZ. So sort of arguing that the location of the rain belt is inextricably determined by the flows, sort of the planetary scale flows of energy north and south, given your forcings and other things. Right, we'll cover all these between the two of us. Okay, so now we're recapping the whole thing. Again, I hope I didn't lose you guys entirely and that you can stomach at the very end of the day. It's kind of some pretty much entirely just heavy theory. The tropical general circulation, for our purposes, is the time mean, zonal mean, and seasonally varying circulation. On our rotating, spherical, seasonally forced Earth, this amounts to the Hadley cells. And those cells descend in the subtropics pretty much year round. And their ascent is more seasonal. It basically follows the sun towards either summer hemisphere. I didn't say this, or I didn't show this whatsoever, but sort of the lead back into the real monsoons here is that you combine these arguments where you treat the whole system as homogeneous, at least its boundaries. You combine these arguments with Earth's continental configuration, with the oceans, topography, et cetera. Skipping over incredibly important details, but that is what it then gives rise to the constellation of the individual monsoon systems, as well as the oceanic ITCZs and the regional subsidence zones sort of opposite those seasonally. And I think I'll stop there. Okay, thank you.
Any questions? Okay.
I think my first question is just like, when we're defining the tropics, I think there's always like different mechanisms to define the tropics, either the descending branch of the Hadley cell or the region where you're changing from RCE to radiative advection equilibrium. Is there like a formal way or what's like the best way to define the tropics?
I think the second question, what's the best way? I think that depends on the question at hand, right? And then the first question, is there a objective way? No, I don't think so. I think it's a good question because it's worth keeping in mind. Tropics, subtropics, extratropics, these are labels, right? These are things that these are concepts that we apply to the system because it helps simplify our thinking and make it more amenable to our analysis. But, the Coriolis parameter, 2 pi sine phi, that's just a continuous, that's very smooth, right? There's no obvious boundary between a strongly rotationally influenced extratropical regime versus a quasi non-rotating regime, which is the deep tropics. You might think, well, what about the Hadley cells? You have this edge, right? There, right? But even that is itself a conceit, right? The descent is occurring over, tens or 20 degrees of latitude. And whether you define it in terms of the stream function or the zonal winds or the jet stream or any of these other things, you get different answers, right? So it's that these edges you should think more as sort of signifying in some way a broader zone, right? Rather than a single latitude. So yeah, that helps.
Do I have time for another question? Yeah, the other one is about the ITC and how we define that like on the continent side, because I know that most of the people use precipitation for locating the ITC, where like the name itself have like the convergence there. And if you go like for precipitation maps near the continents, like for example in South America, you just have like big jumps because of the Amazon rainforest or other resources. So yeah, I think how we define the ITC over continental regions.
I think it's sort of a similar answer to the first question, which again, that's good questions, don't get me wrong. The zonal mean ITCZ, again, defining it, what is that? It's a concept that we've created, right? And so the rain belt, even if you were on a aquaplanet with no zonal asymmetry, the rain belt isn't, a delta function in terms of width, right? There are several degrees latitude the precip spans, right? So you can hope to define a center meaningfully, but even that's not totally characterizing it. And that's all the more, it's even more an issue when you get to the real Earth with the rain belt taking an entirely different character over the continents, the monsoon regions versus the oceanic, sort of more narrow ITCZs, right? So yeah, this is like helpful as a starting place, but then very soon, once you get into the details of the NAM or any of the other individual, you need to be able to jettison this at some point. Yeah.
Thanks.
Okay, maybe just a quick philosophical question. Is the Hadley cell the cause of Earth's deep convection and the circulation, or a result of deep convection? Just thinking like in conservation of mass type arguments and energetic arguments.
I think you would. I think they're inherently coupled, but if you had to give the nod to one or the other, right? The RCE cases, right? Doubly periodic RCE. There's convection. There's no Hadley cells, right? So in that way, you could argue that maybe you should think of those as the more sort of fundamental. Could there be a Hadley cell without convection? I don't think so. Right. Yeah. Yeah. Good question.
Kerry Emanuel was my academic grandfather, so I was familiar with And Isaac Held. I worked with the Held Suarez model
Oh, nice.
for my PhD.
Yeah, as you can tell, I'm one of the Isaac fanboys. So.
Okay. I don't know how much of a flip.
Oh yeah, we're ferocious.
So I guess the idea will be, I don't think we have any other things coming up right now. So if you come back tomorrow around 9, well, before 9, right? Oh, is that what we're doing? Oh. Oh, I'm sorry. My ice is broken. Okay, so I guess that means that we're having something out here. Is that the idea? You'd think I would know, right? Okay. What was that, Jorge? ¿Cuál fue la idea? ¿Qué vamos a hacer? No, no, el otro Jorge, atrás de ti. Yo no soy el mandamás. Okay, so let me see. If there is an icebreaker, it means there's something outside. Vanessa, ¿tenemos un icebreaker o cómo es la cosa? ¿Y es alcohol y otras sustancias? Ah, okay. Bueno. Okay, let's break the ice then. So then tomorrow would be starting again at 9 a.m. and